Hey, what's up, everybody, and welcome back to Code Interpret. Today we've the thing is that we've already learned how a computer program is compiled and translated into machine code because that is what the machine understands. Okay, um, it doesn't a computer doesn't understand the human readable programming language that we write. So whatever we write in our scripts is for our own convenience and for the sake of our own understanding. Right? So similarly, everything, all the data in the computer is stored in bits. Every single thing in our computer is stored in bits and binary. No matter what it is, whether it's a picture or characters, alphabets, numbers, all of that is stored in binary bits, is converted into machine language. And the smallest unit of the data that is stored in our computer is called a bit. Okay, and the bit consists of only two states. Each state is either a zero or a one. Okay. So if it's a zero, zero is considered to be false and one is considered to be true. Okay. That's how the computer reads the binary code. So every time it sees a one, it understands that it's true. Whenever it sees a zero, it understands that it's a false. Okay. So another way to look at it is to consider zeros and ones as circuits in the computer. Okay. And the circuit has only two states. It's either on or off. So whatever is easier for you to remember. So let's look at numbers and how they're stored and calculated and converted back to decimal numbers. Okay, so if we have a variable that has number 65 and we want to print the variable, it will obviously print 65. Okay, but what's happening over here is that it's taking this variable and storing 65 in the memory block, and then is converting it into a binary language, which is the machine language. Okay. And then in order to get it printed back on the terminal, it converts it back to a decimal or a human readable format. So this is a human readable format, so we only understand 65. Okay, now if you want to have an example of what a binary looks like, it actually looks like this. Okay, this is what machine code is. It's just a bunch of zeros and ones. Okay, and the or you can call it a set of instructions. Okay, now if we were to try and understand what this says, it would be really difficult to decode a long list of zeros and ones. But if we look at an example of 65, that's a lot easier to calculate. So the thing is that now what we're going to do is that we're going to convert 65 into binary, and let's see how to do that. And that will basically help you understand what binary is. Because the binary works from the right to left. Okay, the right being the least significant bit and the left being the most significant bit. The most significant bit refers to a number that has the highest value. Okay, and since all of these are zeros and ones, we know that zero is for false and one is true. So if it's false, that means whatever number it would denote or decode, it would decode it as a zero. Okay, that's step number one. Step number two is, since it starts from you start reading it from right to left, the first number has a power of zero. Okay, and the power keeps increasing and it increments by one. So it becomes zero, one, two, three, four, five, six, seven, and so on. Now, why is two over there? Two is there because binary has a base value of two. and since we're converting 65 into a binary code, we will use the base of 2. Okay, so 2, any number raised to the power of 0 would give you a 1, but since this is 0, this 0, it would be read as a 0. Okay, all the zeros would always be read as a 0, as nothing. Okay, and 1 would be read depending on its power. Okay, so if we're trying to read or trying to convert this into a number, into a decimal number, we'll have to see what is the position of this number. The position is starting from the right is the fifth, and because it starts from 0, this would have a power of 4. So 2 raised to the power of 4 is 16. Now if we want to convert 65 into a binary code, how do we do that? So we know from here that 2 raised to the power of 6 is 64. Okay, and then we just need another 1 to make it a 65. So all the other numbers would become 0. Okay, and this would be 1. This would become 1. Any number before preceding that, or on the left hand side, would all be zeros, and all the numbers in between will become zeros. And as long as we have 2 raised to the power of naught or 0 is equal to 1, so we know that 64 plus 1 is 65. So the code would be 0 1 0 0 0 0 0 1. Okay, so this is how we can write it as 0 1 0 0. You leave a space in between to make it more readable. 00 0 1. Okay, so the first one is has a base of 2. A raised to the power of 0 would give us a value of 1. Okay, and then all other would be zeros. Okay, so we can just keep adding them. Plus 0, and then plus another 0, and plus another 0, and this would be a 64 and a 0. Okay, so each number decodes into an equivalent decimal amount. Okay, so the first 0 from the left, or if we start from the right, which is actually the right way to read it, so that is 1, because 2 raised to the power of 0 is 1. And then all these are zeros, so we have 3 more zeros here, and then 2 more zeros, and then comes this one, which is 2 raised to the power of 6 is 64. So therefore 64 plus 1 becomes 65. Okay, so another way to write this is you can use 0b. B represents binary. Okay, and then copy and paste all of these numbers here. Okay, this is your binary code. This is the binary code for 65. Okay, so what we've done here is that we've converted a decimal number into a binary code. Okay, now if we want to check, if you want to check whether we're right or wrong, what we can do is that we can use a print function and another function that is called binary. It's a built-in function, and then inside the brackets you write 65, and let's check what it is. And there you go. It has the same B, 100, and 000 and 1. So we're right. Okay. So let's have a look at another number. Okay. So let's say let's just have a look at this diagram. So let's say we we're trying to convert 43. Okay. So let's try and convert 43. For 43, we need a 3 in the beginning. Okay, so this is going to be 1 and 2, 0, and 0, and then uh, okay, so 2 raised to the power of 3, this is 1, 2, 3 is 8, so we need an 8. 8 plus 3 is 11, and then we need a 32. Okay, let's just have a look at, so the sixth number is raised to the power of 32. So 32 plus 8 is 40, 40 plus 2 is 42, 42 plus 1 is 43. Okay, so the sixth number, this is 0, 1, and then 0, 0. Okay, so a nice way to do the calculation is to break it into groups of 4 bits. Okay, 4 bits here and 4 bits here. So this becomes, the first one becomes 1 plus 2, because 2 raised to the power of 1 is 2, plus 0 plus 2 raised to the power of 3 is 8, plus 0 plus 32. Okay, and that would give us 43. So if we were to represent it in binary code, it would look something like this: 1011. Let's try it out and use the bin function again. 43, and there you go. 101011. 101 011. Okay, so it's okay, you can add as many zeros as you want. Okay, now if I wanted to convert this back, so let's say 0 b 101011. See, if you wanted to convert your binary code back to a decimal form, simply use the letter B, and the first one should be a 0. So all the numbers after the most significant bit are all zeros. Okay, but they're all imaginary. You don't need to write all the zeros. So you can just add 1 0 at a B, and then what do you call, write this code, the binary code. Just copy it and paste it over here without a space. All right. Okay, so if we have 0b 0, see, so no matter how many zeros you add over here, it, because it reads, the computer reads all the numbers from starting from the right, which is the least significant number. Okay, it would always return a 43. Okay, so it doesn't matter how many zeros you add over here, as long as you start from the right hand side. Okay, which is the rightmost or the least most significant number, and then move towards the left. So no matter how many zeros you have here, it would still calculate and convert it back to 43. But if you have zeros over here in between, then you basically changing the position of this one. So you need to make sure that if you're adding zeros, you add the zeros after the most significant number. You can add as many zeros as you want. All right. Okay. Thank you.